Welcome, students. We want to continue our discussion about extreme values of the function. We discussed about local maximum and local minimum in the last class. Today, we want to talk about absolute maximum and absolute minimum. Yeah, sometimes it's also called global maximum, global minimum, or sometimes we drop the adjective absolute. It is clear when you say maximum or minimum, you're talking about absolute maximum and absolute minimum. So, so then the first question is, does the absolute maximum and minimum exist? So recall for function of one variable. So f, a continuous function from to R has, so so we have a continuous function. So if we take a continuous function on a closed interval, if f is a function from closed interval ab to R and is continuous, f has absolute maximum and minimum. We want to have a similar result for function of two variables now. So what we'll try to do first is we will generalize this idea of closed interval. So what could be a reasonable generalization of closed interval in function of two variables? That means in R2. So for that, we have the following definition to start with. So what is the boundary point? So boundary point of D, which is a subset of R, is a point AB such that every disk within this with the center AB contains point of D and also points that are not in D. So every open disk, right? So this disk is open. So think about it in the following way. So let's take this as D. This is our set D. So if we look at a point here, we can draw an open disk such that this point, when you draw a disk around it, it's completely inside D. So this is not a boundary point. Whereas if we take this point here, so this point is a boundary point. It kind of gels well with our idea of of the boundary, right? So again, so what you do is you draw a disk around AB. So that's this point. If this point is AB, if no matter what size disk you draw around AB, containing AB, it will always have points which is inside the D coming from this part here, right? Here, um, and the points which are not in the D coming from here. Okay? So such a point is called boundary point of set D. Now, what is a closed set? So closed set in R2 is one which contains all its boundary points. So for example, what could be an example of this? So let's take a circle. Now, circle contains all its boundary points, right? Because if you take any point on the circle, you draw a disk, it will consist of points which are inside the or in are from the circle and also from outside the circle. Another example could be, say, a square. This also contains its boundary points. Another example is a shape like that where the boundary is included. So this also contains boundary points. So these are all examples of closed sets. Yeah, you can have inside. Okay. Now let me give you an example of not closed sets. So consider the following. Consider the following. So this set is not a closed set. Why? Because, so what is this first of all? This is basically, take, for example, let me be precise. So take x squared plus y squared strictly less than 1. So it's essentially a circle of radius 1 with the edge removed. So if you want, I can draw this in the following way. So this is essentially this circle here with the edge not there. Now, this is not a closed set, not closed. So why is it not closed? Because if you take a point on this point is a boundary point, right? So this point is a boundary point. Why? Because if we draw any disk around it, it will intersect outside the set and inside the set. It will have points which are in D and also points which are not in D. But so this is a boundary point. But since we have excluded the outside of the circle, this is not in your set D. So it's not closed. Okay. So this is not a closed set. Similarly, we have concept of bounded set. So bounded set in R2 is basically a set which is within some disk. So this set, say for example, is bounded. Why? Because I can draw a disk. So this should be thought of as a circle with the boundary removed, right? So this, I can draw a disk in it in which basically this set is contained. So this is a bounded set. So D is bounded set in R2. Now, for example, what is not bounded set? Take, for example, in R2, take x-axis. This is not bounded, right? So x-axis is not bounded. Why? Because, well, you can't draw a finite disk in which this line will be contained. So this is not bounded. All right, so now we are ready for the version of extreme value theorem for function of two variables. So let f be continuous on a closed bounded set of R2, then f attains absolute maximum and absolute minimum at some points x1, x2 and y1, y2 in D respectively. So this is the extreme value theorem. So note that the generalization, the reasonable generalization of closed interval in function of one variable, the reasonable generalization is basically a closed and bounded subset in R2. All right. So now, where do these occurs? Right. So the question is where to. The question is how to find absolute maximum and minimum of f of xy on D. Yeah. What is my D? D is this D is closed and bounded. So this is a two-step process. So step one, find values of f on critical points inside D, and then find, so step one, step two, find values of f on D And then step 3, compare from 1 and 2 to find max/min. This is essentially what you did for the function of one variable as well. Recall, for function of one variable, you had critical number, you found out the value of function at the critical number, and then you found out the value of the function at the endpoint. In our case, we'll have to understand the maximum or minimum value of function on the whole boundary. So let's embark on this example. So step 1, find critical numbers, right? So we need to find for critical number, for critical point. So let's compute the critical point of this function. So critical points are, take fx, which is 2x, this becomes 0 minus 2, and take fy, which is again 4y minus 4. So fx equals to 0 implies x equals to 1, and fy equals to 0 implies y equals to 1. So therefore 1 1 is only critical point. 1 1 is only critical point inside T. And we need to find out value of f11. F11 is minus 2. Now let's consider our domain D. So we need to draw domain D. So first one is, we have 0 to 2. So 1, 2, and then we have 1, 2, 3. So we have, this is our, so this is our boundary now. The boundary is these lines, so L1. So now step 2, so let's call this as L1, L2, L3, L4. So now step 2. Now step 2, we are interested in what? At boundaries. So along L1, so we get what? Along L1, what do we get? We have y is 0, and hence we get what? Therefore f of x0 is going to be, wherever there's x you put 0, sorry, wherever there's y you put 0, x square minus 2x plus 1, which is same as x minus 1 the whole square. And you're looking at this function from 1 to 2. So now we need to find out the maximum value of this function along the boundary L1. So now we have reduced ourselves to the function of one variable. So either we basically do calculus of one variable on this function. However, the function turns out to be very nice and straightforward. So what we do is the following. We'll say that this has, so we can clearly see that this has maximum value when either you have x equals to 0 or 2, right? When x equals to 0 and 2, And what do we get? We get basically f of 0. So x is now 0. So 0, 0 is f of 2, 0, which is 1, and has minimum value when x becomes 1 at x equals to 1 of what? What is the minimum value? F of 1, 1, which is going to be, sorry, f of 1, 0, which is going to be 0. So we have just fixed this along L1. Now we'll talk about along L2. Now along L2, what do we have? So what is, so this is 2, this is 2, 3, this is 2, 0, right? So along L2, what we have is x is equal to 2 and your y goes from 0 to 3. So this is along L2. So now we are taking care of the second boundary. That way we'll have to take care of all the boundaries of it. So we get along L2, we get that. So we have f of 2y is going to be wherever there's in this function, I'm going to put instead of x, I'm going to put 2. So I get 4 plus 2y square minus 4 minus 4y minus 1. So this is going to be y square minus 4y plus 1, y going from 0 to 3. Now I can complete the square and look at the maximum or minimum, or I can employ, basically, let's call this as g of y. Now I'll use the function of one variable. So what is g prime y? So g prime y is equal to 4y minus 4 equals to 0. So this gives me y equals to 1. And now what I'm going to do is I'm going to check at the, so g of 1 is equal to, g of 1 is equal to f of 2, 1, which when I put this value, I get, so g of 1 is 2 minus 4 plus 1, so is minus 1. And g of 0, I need to check at the endpoint as well, because now I'm in the function of one variable, right? Function of one variable. Okay, so I'm basically reduced my problem to function of one variable now. So what do I get? G of 0 is 1, and g of 3 is equal to, so 2 times this, so it's going to be 3 square is 9, so 2 times 9 is 18. 18 minus 12 is 6. 6 plus 1 is 7, which is same as what is, so therefore what do I get? I get, what is the largest value here? The largest value is g of 3 and the smallest value is g of 1. So therefore we get what? What are the values we got from here? The values of importance for us is f of 2 minus 1 is negative 1 and g of 2, 3 is 7. F of 2. Okay, so now let's go along L3. So along L3 here, we have, along L3, we get x, we get y equals to 3, and our x goes from 0 to 3. So this is along L3. So then we have f f of x3 is going to be x squared minus 2x plus 7. Now, I mean, instead of doing the function of one variable, thankfully this is a quadratic equation for which you can quickly find, we get what? X minus 1 the whole square plus 6. So where x is between 0 and 3 has maximum value. What is the maximum value? Maximum value will be at, when x is 0, you get 7. And when x is 3, so x is 0, you get 7. And when x is, so we get x is 0, we get 7. And x is 2, we get 7. When x is 3, sorry, our x is between 0 and 2, not 0 and 3. So we have, right? I mean, x values are between 0 and 2. So we get, in this case, the maximum values are at 0 and 2 both, right? So has max value at 0 and 2, and min value is at what x? Min value at x equals to 1. So therefore the points of importance for us is f of 0, 3 equals to f of 2, 3, which is going to be 0, 3 of 2, 3. So you get 7. And f of 1, 3 is going to be 6. Now comes the last one along L4. So now L4 is this line here. So for along L4, what do we have? We have our y, our x is 0. Along L4, we have x equals to 0 and y is between 0 and 3. So therefore we get what? So now for L4, we get, along L4, we get, so let me put in function instead of x 0, y is y. So we get, this simplifies to 2y squared minus 4y plus 1. So we get 2y squared minus 4y plus 1. And with basically your y going from 0 to 3. And this we have already seen earlier. This is exactly same as, if you look at this function, this is exactly same as this one here, right? So therefore we have, which has max value at, so we got max value at 3, that is f of 0, 3 equals to 7. And min value at min value, so 0, 3, what are the other places we achieved this? So we have f of 2, so we get the max value is 0, 3, and we get min value at y equals to 1, right? Min value at y equals to 1, where we get what? We get f of 0, 1 is equal to 2 minus 4 plus 1, which is going to be minus 1. So now we have to compare the values. So let's compare all the values we got. So first value to compare would be well, one value to compare. These are values we need to compare. Along L2, we got maximum and minimum to compare here. And we get along this thing, we have these values to compare. And along L4, we have these values to compare. So among all this, which is the largest value? So then we are in step, this was step 1, this was step 2, step 1, step 2, and now let's step 3, comparing all the values. So step 3, if we compare all these values, you'll see that the largest value is basically 7. So we get what? F of 0, 3, going backwards, F of 2, 3, and then where else? F of 2, 3 is, that's all, is 7, is absolute max, maximum, and what is absolute minimum? So let's see. We have the lowest -2. This goes only -1. Okay, so seems like -2 is the least value, which happened at the critical point, right? So f of 1 minus 1 equals to -2 is absolute minimum. So this is how we find absolute maximum and minimum of a function. So now let's look at the other example. Namely, we had the following. Consider f of x. So find absolute maximum slash minimum of f of xy equals to xy square on D, which is given by x greater than equal to 0, y greater than equal to 0, and x square plus y square is less than equal to 3. So let's first draw this. So when we draw this, it will essentially be so we are looking at the first quadrant of the circle. So this is our region where we want to maximize and minimize our function, right? So let's work on this one now. So f, this is your region D. Okay, so it has three boundaries, right? It has three distinct parts. So it has these three different curves as boundary. That's what I meant by three boundaries. It doesn't have three boundaries, but three distinct curves, which are the boundaries, right? So let's work on this problem now. So first step 1 is to find the critical number and the value of the function at the critical point. So critical point first. So let's take fx equals to y square and fy equals to 2xy. So if x equals to 0 implies y equals to 0. Now note that y equals to 0 does not lies inside, right? So it does not lies inside D. So when you say inside D, it has to lie in the interior of D. Does not lies inside or in interior of D. So no critical number. So there is no critical number. No critical number inside D. Okay, so no critical number inside D. So we don't need to worry about the critical point. Yeah, we are in 2 dimensions, so it's not critical number, it's critical point. So no critical point inside D. So now all we have to do is study the function along the boundary. So let's call this as L1, L2, L3. So let's see along L1. So this point is going to be 0 square root of 3. This is going to be square root of 3 comma 0. So along L1, what we have is we have x equals to 0 and y goes from 0 to square root of 3. So what do we get? So x is 0, so we get f of 0 y, which is going to be 0. Well, it's a constant 0 function, so nothing really interesting happening. Along L2, y equals to 0 and x is between 0 and square root of 3. Again, we have f of x 0 is 0. So nothing really interesting. No maximum or minimum discussions can occur. Every point is maximum and every point is minimum. Okay. Now along L3, now that is slightly interesting. Along L3, we have what? We have, so what is the equation of the circle? So the equation of circle is, for the upper part is x squared plus y squared equals to 3, or we get y equals to square root of 3 minus x squared, because we are looking at the positive part. So along L3, we have y equals to 3 minus x squared square root. And again, your x is changing from 0, square root of 3 to 0, right? So we can say our x is between 0 and square root of 3. So these are your L1, L2, and L3s. So along L3, this was along L2, along L1. So now along L3, let's see what do we get. We have f of x, instead of y, I have 3 minus square root of x squared. So 3 minus square root of x squared. This is going to be, so instead of x, we have x. Instead of y, we have xy squared. So we have 3 minus x squared. That is same as 3x minus x cubed. So now we have a function. So now we have a function of one variable. X is between 0 and equal to square root of 3. Now the best way to do that is to maximize this using function of one variable. So consider g prime x. G prime x is 3x minus 3x squared, which equals to 0, gives me x 1 minus x squared times 3 equals to 0, which gives me x equals to plus or minus 1. But x cannot be negative, right? Because we have restriction. The restriction is that x is greater than 0. So this implies x equals to 1. Discard x equals to minus 1, since it does not belongs to, since minus 1 does not belongs to D. So we have minus 1 does not belongs to D. So we'll only be interested in 1 at the moment. Now, so let's see. So what is g of 1, which is same as f of 1 square root of 3 minus, so square root of 2, and at endpoints g of 0, which is f of 0 square root of 3, and we have what, g of square root of 3, which is going to be f of square root of 3 comma 0. So well, clearly when they are 0, well, it will lead to 0, right, because multiplication. So g of 1 is we have 1 times 1 square root of 2 square, 1 times square root of 2 square, which is 2. So if you compare all these values, so we compare these values, we'll see that the maximum value is f of 1 comma square root of 2, which is 2, and minimum value is f of 0 root 3, f of root 3 0 equals to 0, and also so a minimum value occurs and also occurs along L1 and L2. Yeah, so you see at all these boundary points you get minimum values. Okay. Another interesting example would be find absolute maximum and minimum of your function f of xy, which is x squared plus y squared minus 2x on D, where D is a closed rectangular region with vertices 2, 0, 0, 2, and 0, minus 2. So for that, we need to first draw this to get a better picture of what is happening. So we have, so the points are 2, 0, so 2, 0, which is this point here. And then we have 0, 2, which is this point here. And then we have minus, so 0, minus 2, which is 0, minus 2, which is here. So here in this case we have, this is our, we need L1. So this is L1, this is L2, and we can name this as L3. So L1, L2, and L3. So now again we have to do the same thing. So let's proceed with this. So first of all, step 1, find critical point of f, y in interior of T. So we'll do fx, which is 2x minus 2, and fy, which is 2y. So fx equals to 0 implies x equals to 1, and fy equals to 0 implies y equals to 0. So therefore, consider 1, 0 is a critical point. Does it lies inside the, because what is our region D? Region D is this closed region enclosed by, so this is our region D. So this is region D, including the boundaries. and 1 0 lies inside, right? So 1 0 lies inside is the critical point that lies in the interior of D. So now we'll compute quickly f of 1 0, which is going to be, when you substitute 1 for x, you get 1 minus 2, which is minus 1, and so we get minus 1. So this is a value which we'll try to compare later on. So we got one value, which is the f of 1 0. Okay. Now step 2. So step 2 is to maximize at the boundaries. So step 2, maximize on boundary. So again, we can decompose boundaries into three curves as we see L1, L2, and L3. So what is equation of, sorry, this is 0 minus 2. So we need to find equation of this line. So how do we go about it? So equation of a line, in this case, can be written very quickly. So L1 is given by x over 2 plus y over negative 2 equals to 1. And that would mean that we get this implies we get x plus y, or rather we get y equals to so minus 2 will make it minus x, so minus x goes on the other side, becomes x minus 2, and your x is between what values? So 0 to 2. Note that it's easy to find equation of line if you make the intercept a and b. These are non-zero values, then the equation of line is x by a over y by b equals to 1. Okay. So now along L1, I need to maximize this. So what do I get? So along L1, I have f of x comma x minus 2 is going to be x square plus x minus 2 square minus 2x, which is going to be, on simplification, 2x square minus 6x plus 4. Now, either you make a function of one variable out of it and find the critical point and look at the endpoint, or you can complete the square to get 2 times x minus 3 by 2 the whole square minus half. So when you write it like this, you can clearly quickly say what is the maximum value and minimum value. So in this case, the quadratic attains minimum is always at the vertex because the sign a is positive. Minimum value is at x equals to 3 by 2, and we have f of 3 by 2, x equals to 3 by 2 comma x minus 3 by 2, so 3 by 2 minus 2, which is minus 1 by 2, which is going to be minus half, which comes from here. All right, I'm not doing this computation separately. And the maximum value is at the end, maximum value is when you have, basically this is 0. So when you have 0, you get 0 minus 3 by 2, which is 3 by 2 square. So we get maximum value is f of 0, and when you put x equals to 0, you get the y value is minus 2, which is equal to 4. Okay, so these are the two values we'll compare. Now along L2, so let me just color these things. So this was along L1. So along L1, this is what happened. This is along L1, and the points to consider, the values to consider are this one as a maximum value and this one as a minimum value. From the critical point, we got that value here. Okay, now we need to consider along L2 and L3. So along L2, now what is the equation of L2? Same way, this point is 0, 2, so it's going to be x by 2. L2 we have x by 2 plus y by 2 equals to 1, or we can write it as y equals to 2 minus x, and your x is again between 0 and 2. So this is your L2. Okay, so now let's compute what happens along L2. So we have f of x comma 2 minus x. Upon simplification, we'll have, that's what is your function? So we have x squared plus 2 minus x the whole square minus 2x. And if you look at this, this is same as, if you look at this, this is going to be same as 2x squared minus 6x plus 4. The same as, so again, this is exactly the same situation as L1. So as attains minimum value at x equals to 3 by 2, that is f of 3 by 2 comma minus 1 by 2 is minus half, exactly the same as the function along L1, and maximum value at x equals to 0, we have f of 0 2 is equal to 4. Now comes along L3. So along L3, we have now L3 is what? L3 is simply x equals to 0 from minus 2 to 2. Along L3, x equals to 0 and y goes from minus 2 to 2. So let's sub in that value. So f of 0y is going to be, when you put 0y, you get y square. And again, if it's square, we can quickly tell has max value at at what? At plus or minus 2, and f of 0 plus or minus 2 is simply 4, and min value at 0, that is f of 0 0, is simply 0. So now this is along, this was your L3, and the values we got are these. So this was step 2. Now step 3 would be to compare these values, right? Step 3, compare. So what are the maximum among all these? Let's see. So first we got, for critical point, we got minus 1. Critical number, we got minus 1. For critical point, the value was minus 1. Then we have 4 here, minus half. Nope. Here we have 4 again. We have 4 here, 0 here. Okay, so clearly 4 is the largest value. So we have f of 0 minus 2, 0 plus or minus 2. Where else do we get 4? Yep, that's all. 0 plus or minus 2 equals to 4 is maximum. And what is the minimum value? So minimum value here we get 0, but minus half seems to be the smallest. Actually not. We have f of 1, 0 is minus 1. So that is the smallest. And minimum value is absolute minimum is absolute minimum. So this does the whole, solves the whole game. Thank you for your attention.